Hello, my name is Roy Simpson. I'm an instructor of mathematics at Cosumnes River College in Sacramento, California. This lecture is based on intermediate algebra, still a kind of a review of intermediate algebra, but we're verging on the more difficult parts for the review. Specifically, we're going to focus on solving applications involving linear equations. This is a subtopic of algebraic equations. This is all about word problems, basically. How do you solve word problems? Now, their word problems are all throughout life and all throughout mathematics as well, especially intermediate algebra on up. And what you want to develop is a way to kind of solve any type of word problem presented to you, or at least an approach to help you try to solve any problem placed before you. And in a previous lecture, I've actually mentioned a method to do this. I will repeat that method in a moment. But before I do, let's talk about the prerequisites to this section. You must know arithmetic and elementary algebra. Obviously, it's assumed that you know everything from elementary algebra, which should mean that you actually know how to do these problems. But good to review anyway. You should know how to solve a linear equation. If you don't, see part 1 of this lecture. And you should know how to evaluate expressions and know what an expression is, how to simplify expressions. Now, if you recall from a previous lecture I've given, there is a method. It's called Pelleas Method. Let me actually write that down. I didn't write that down before. And the first thing we always do when we're given an application or a word problem is we read the problem and understand the situation. Sometimes it helps out to draw a picture, right? Just to help kind of cement our knowledge of the situation. Next thing we do is we state what the unknown is. So you're looking for what is the unknown. You kind of say, well, we're looking for distance in this case, or we're looking for how long it takes for the ball to hit the ground, or something like that. And you choose a variable for that unknown. This is what I call the let step, because you usually let v equal the velocity of the ball or something like that. And that way, when you label your unknowns like that, you can always refer back to them when you read your solutions later on. Third thing you do is you write several algebraic expressions for the situation using the variable, or you could write several algebraic equations, whichever. So maybe I should say or equations here. I know it's really small, but what are you going to do? And then you use these algebraic expressions to form an equation and solve the equation. Generally best to also check your answer. So when we go through and we solve some upcoming word problems, I'm going to follow these steps. Step by step, go through and mention each of them. So for our first example, you're going to consider buying a new car. And you've narrowed down the choice down to 2 vehicles. In either case, your parents are going to pay for all the extra stuff like insurance and maintenance, repairs, all that fun stuff. So all you have to consider now is the actual cost of the car and how much it costs to drive it for fuel. The first car is a Honda Civic Hybrid. That costs about $23,500. And then you kind of figure out through some level of mathematics that it's 4 cents a mile that it would cost you for the fuel because of the miles per gallon that gets. A second vehicle you're considering is a Honda Fit, which costs $14,550. It costs 6 cents per mile that you drive it. The question is, how many miles must you drive before the cost of owning the vehicles is exactly the same? So I've read the problem. So step 1, I've read it. I understood what's going on. Second thing I need to do is mention what are the things I'm looking for, and that's usually in the last sentence. The last sentence kind of has this hint, how many miles. So a good variable for the number of miles is m, so I'm going to maybe say let m equal number of miles, and I'm not just going to keep it like that, number of miles. I'm going to say let m equal number of miles when owning costs the same, or something like that. And the reason why is I think that it's just important to be very specific with your variables. Okay. The third thing we need to do is write some equations here or expressions, whichever. So I see the first car costs me, so car number 1. And in fact, you could say it's the Civic. For the Civic, we have an expression for how much it costs to own that. It's $23,000. And the wording says, and 4 cents per mile driven. The and 4 cents per mile driven means you're going to add on or tack on 4 cents for every mile you drive. And we're letting M equal the number of miles, so 4 cents times M. If you only drive it 1 mile, it costs you 23,504 pennies. So on and so forth. For the second car, and since I've written car number 1, I'll write car number 2, but it's the Honda Fit. It's actually a cheaper car. That's very attractive, right? $14,550. And it costs you 6 cents per mile. So a little more expensive for fuel because the fact is it probably gets less miles per gallon. That's probably why. So these are the costs of owning the car. And we want to know, when are the costs the same? So when are these the same? Well, they're the same when they equal one another. So that's when 23,500. By the way, I'm in step number 4 at this point. 23,500 plus 0.04 m is equal to 14,550 plus 0.06 m. Once I get into a mathematical equation like this, I forget about the problem. I go ahead and just move on with life and just focus on this equation. So I think, okay, now solving equations, I know the first thing I do to solve an equation is I clean up each side. And in this case, both sides are cleaned up. There's no parentheses on the left or the right. And there's no way to combine like terms on the left. There's no way to combine like terms on the right. Second thing I'm going to do is move variables to one side. Move variable terms to one side. So it looks to me like if I subtract 0.04 m from both sides, that's a good choice. You only subtract it once from each side. I've seen students subtract it twice for some silly reason. This implies our equation becomes 23,500 equals 14,550 plus 0.02 m. And once you're pretty good at using my technique for solving linear equations, which I've mentioned in the past, you kind of do this very quickly. But I'll still use my technique just to kind of mention it a few more times before we start using it quickly. The technique that I use for solving linear equations, if I only have one version of my variable, I say, well, if they didn't tell me exactly what the variable is, in other words, they didn't give me m equals 5, I have to ask myself, what is m? They did something to it. So what happened to it? Well, somebody took it and multiplied it by 0.02, and then after they tied it up in that little knot, they then added to it 14,550. So to undo that, I'm going to, well, it's like untying a shoe. You start with the last thing that you tied. The last thing we tied was we added 14,550. The opposite is subtracting 14,550. And the next thing we untie is the multiplication, which is a division. So I'll apply these things. I'll subtract 14,550 from both sides, and I will then divide both sides by 0.02. 14, let's see, we had 23,500 minus 14,550. So that'll be the subtraction process, and then we're going to divide that by 0.02. So we get 447,500. And now I can put that in context of the problem. How many miles must you drive before the cost of the ownership is the same? 447,500 miles. At that point, the cost of owning the cars is exactly the same. So really, not very many cars actually go to about 500,000 miles. So it might be to your benefit to stick with a Honda Fit because it'll be cheaper that entire time. Of course, there are a lot of other things that go into calculating the cost of a vehicle, the insurance costs, all those, the maintenance costs. But notice in the beginning of this problem, I said that those were kind of paid by somebody else. So we read it, understood it. We allowed M to be the number of miles we were talking about. And then we developed a couple expressions and then put them in an equation and solved them. Now, I really tire of math textbooks that have sort of just the bland problems. In California, there is a medicinal marijuana law that, well, it's not really a law. They allow them to run medicinal marijuana facilities. And a lot of authors would spend time avoiding topics like this because they think it's a civil no-no, I suppose. But the fact is, it still makes for great math problems. So I just think I make math problems out of anything I possibly can. And here's just one of the many that you can make math problems out of. And this is actually a pretty interesting math problem anyway. The 420 connection, a medical marijuana facility, finds that when it charges P dollars for an ounce of medicinal marijuana, it can sell 55 minus 1 over 20p ounces per month. By the way, because I typed that up, that is supposed to be 55 minus 1/20th times p ounces per month. So that's what it can sell. Okay. In fact, I'll call that, instead of sell, maybe I'll call that the demand. That's what people demand. Okay. People demand that from the 420 connection when they charge P dollars per ounce. Okay. On the other hand, they have somebody that supplies them. This business, 420 Connection, has a supplier that grows all the medicinal marijuana and then supplies it to them. And let's say their name is Green Growers Incorporated. Just sounds like a funny name, so I just put it on there. So the Green Growers Incorporated say, hey, if you're going to charge P dollars per ounce, or if you're going to pay us P dollars per ounce, we'll supply you with 15 plus 1/4 times P ounces of medicinal marijuana for prescription sales. So in other words, the supply that they're given, they're going to give to the shop, is 15 plus 1/4 times P. So you have a demand by the public and the amount that would be supplied. Notice the demand by the public, by the way, starts at 55. And that's ounces per month. So 55 ounces per month at this facility is what it starts at, but it drops according to the price. So the higher the price, obviously the demand will lower. The supply, on the other hand, the supplier says, listen, I'll give you 15 ounces per month, but if you want to give me more money, I'll give you more. So I'll add another 1/4 ounce per dollar that you're willing to sell it for. So this is kind of a nice way to kind of think about supply and demand. All right, so what price should the 420 connection charge per ounce in order to sell out of medicinal marijuana each month? So they want to sell all of what they have. So they have to figure out when their demand from their consumers meets the supply that they have, right? They want those two to be the same. So let me write that in language. We want supply to equal demand. And I'm using a very fictitious situation here, but this works for any type of business model. You want supply to equal demand. You do not want to have more than what people demand, because then you have to pay rent on that. And you don't want to have less than what people demand. Well, mainly because you can make more money if you have exactly what they demand. So here we go. By the way, all of that, I didn't even follow this method. Sorry. First thing, I read and understood what's going on. Read, understood. The second thing was to label the unknowns. Well, they kind of gave us the unknowns in this situation. Let P equal dollars per ounce. All right. So that's really, I mean, they gave us all that. Third thing I'm doing is I create equations, but they kind of gave us that too. So given, this happens every once in a while. We're lucky if they give us this stuff. Fourth thing we're going to do is build an equation involving these, and that's this part right here. Is we want supply to equal demand. Okay, so supply is 15 plus 1/4 p, and we want that to equal demand, which is 55 minus 1/20th p. And actually, I should make a mention here. I kind of didn't know now. In mathematics, well, maybe I should say in physics and chemistry and biology, the case on your variables is very important. So if they start with a lowercase p, you should keep a lowercase p the entire time. I kind of cheated a little bit, and we tend to forget that, so it's somewhat important. Okay. So now I see I have a linear equation. I'm gonna forget about the problem now and or about the word problem and focus on the linear equation here. In the linear equation, to solve that, remember we clean up both sides, but again, both sides are already cleaned up. We'll move variable terms to one side. So in this case, I'll probably move the negative 1/20p to the other side. So I'll add 1/20p to both sides. Which means I have a little fractional arithmetic. And I won't go into my reasoning right now, but there's something I generally do with these problems prior to even doing this step. But I'll just wait for a moment until we're done with the problem, then I'll discuss it. So we have 1/4 plus 1/20th. Those both have p's attached to it. I'm just going to multiply top and bottom of this by 5. So that gives me 5/20ths plus 1/20th, or in other words, 6/20ths, and this reduces to 3/10. Okay. So this is plus 3/10 p is equal to 55. And now I'll solve it. Right? Since there's only one version of my variable, I'll untie that knot. P has just been tied up into a knot, so what has happened to P? Well, the first thing that happened to P, whoever has hidden the value of P in this equation, they've decided to multiply it by 3/10. And after they messed it up doing that, the second thing they did was add 15 to it. So both those operations they performed to confuse us, to basically hide the value of P from us. But we can untie those, and whenever you untie a knot, you start with the last thing that got tied. So last thing that got tied was that positive 15. Untie that, it's a negative 15. And then the step prior to that was a multiplying by 3/10, so we're going to divide both sides by 3/10. Okay, so here we go. We'll subtract 15 from both sides first. And that will give us 3/10 p is equal to 40. And now we'll go ahead and solve for p by multiplying both sides by 10 and dividing both sides by 3, or basically just dividing both sides by 3/10. If you divide both sides by 3/10, divide this by 3/10, you'll see these two, 3/10 over 3/10 turns into 1. I'll divide this side by 3/10. Notice how when I divide by a fraction over here, I write it as a division symbol. And the reason for that is the math is a little bit easier, because you can see, oh, I have 40 times 10/3. And usually people find that to be easier. So that's 400 thirds, which is roughly equal to 133.33. It's not really equal to that, but it's $133.33. $133.33. So if that's what they charge per ounce, I have no idea if that's, I have no idea. I think that might be way low. But if that's what they charge, they'll sell out. And their supply will equal their demand. Now, I did say that I would show you another way to solve this, a way that I would prefer, actually. A way that I prefer to solve it if somebody gives me an equation that looks like 15 plus 1/4 p equals 55 minus 1/20th p, generally after I've cleaned up sides, basically, once I get that step done, I tend to look at this and go, oh, this has just a bunch of stuff I don't like. For one of the things I don't like fractions. So I find the LCD, which is 20 in this case, and I multiply every single thing by 20 by that LCD. So every single term in this equation, I'm going to multiply by 20. So I'll attach a 20 to that. I'll attach a 20 to this. I'll attach a 20 to that, and I'll attach a 20 to this. And while initially it looks like it would be horrible, because the 20 times 15 is not something that a lot of people know offhand, but it's 300. You see what happens, 4 goes into 25 times. And over here, 20 times 55, well, if you don't know that offhand, you can always grab a calculator. That's what I basically just did. It comes out to 1100. And so now look at my equation. Much easier to work with. I'll just add p to both sides to get 300 plus 6p is equal to 1100. Subtract 300 from both sides. And then go ahead and divide by 6. You get the same answer. So that's often what I do when I see an equation. Once I get to an equation that has fractions, I often just multiply both sides by the LCD. It's a good habit to get into and makes your life a little bit easier in the long run. Now back to the typical examples that you'll see in a textbook. You got a couple people that spend some time someplace. Okay, this is like the train leaves the station type of problem. At 2 o'clock in the afternoon, Lynn leaves the mall driving at 45 miles per hour to go to San Francisco. 3 hours later, Sarah finds Lynn's cell phone in her purse and leaves to catch Lynn. What a good friend. 3 hours later, decides to travel off to San Francisco to find her friend. Not realistic at all. Well, let's see. If Sarah drives at 60 miles an hour, how long would it take to catch Lynn here? So this is like I said, not a very realistic situation, but we have a few things that kind of indicate to us what we're going to do here. We have a couple rates. That's what these 60 mile per hours are. They're rates, 60 miles per hour here, and then we have another 45 miles per hour over here. And then the question is, how long would it take? So that's a time. We want to know time. That's a huge indication that we're going to end up using a formula like d equals rt. That's distance equals rate times time. Just have to make a note of that before we begin going through our process. So I read the problem, I understand the problem. I'm not really going to draw a picture for this. I mean, I suppose I could, but it would look like 2 lines. It wouldn't really do very much for me. The second thing I'm going to do here is label the unknowns. I'm going to let t equal time to catch up. Maybe I should even be more explicit. Let's see, time for Sarah to catch Lynn. That's very specific, and that's good. And you'll see why in a moment. Catch Lynn. Okay. And the third thing I'm going to do is write a couple expressions involving this variable time, t for time, and maybe their rates and stuff like that. And this is how I generally do it. I'll write one for Lynn, and I'll write one for Sarah. And you probably have noticed earlier that I did this as well. I have 2 people, 2 expressions. Lynn is traveling 45 miles per hour. Sarah is traveling 60 miles per hour. The time that Sarah has been driving, we said that's t. T is the time for Sarah to catch Lynn. So t is the amount of time that Sarah's been driving. So 60t should be the total distance that Sarah's driven. Lynn, on the other hand, has been driving the same amount of time that Sarah's been driving, but a little bit more. She's actually been driving 3 hours. She had a 3 hour head start. So if Sarah drove 1 hour, Lynn's driven for an hour plus another three for 4 hours. Okay. The way this problem is solved is that you have to think logically. If now, I guess I will draw a little picture. If this is the mall and Lynn leaves, and then 3 hours later Sarah leaves, but they're driving on the same roads. Okay. By the time they catch each other, right here, okay, is where they meet. Let's just say. By the time they catch each other, shouldn't their distances be the same? Shouldn't those two distances be exactly the same? Well, that means that this distance that Lynn has driven should be the same as the distance that Sarah has driven. So 45 times t plus 3 should equal 60t. Now, often when I teach this, I actually don't. This is not technically the method I usually use. It's very close to it, but not exactly the same. I usually say, listen, write an equation. Write as many equations as you can for the situation. In this first case, you have Lynn. She's driven d equals rt, right? D equals rt. She's driven a distance d, and it's equal to 45 because it's her rate, and times the time she's been driving. And Sarah has driven a distance d at 60 miles an hour for t time. But I know that these two distances are the same, so if this d is the same as that d, then these two things must be equal. Writing it both ways, one way or the other, doesn't really matter. It's just thought I'd let you know that you could do it that way as well. Now I'm down to an equation, so let me clean up both sides. I'll distribute this 45. So I'll have 45t plus, what is that, 120 plus another 15, 135. That's supposed to equal 60t. I'll write my little implication symbol there. And now I'm going to go ahead and move all variable terms to one side. I think the right-hand side is a good idea, so I'll subtract 45t from both sides. I'll show that work. So let me subtract 45t from both sides. And that will give me, on the left-hand side, just a regular old 135. On the right-hand side, 15t. And now I'll just divide both sides by 15, so 135 over 15 will equal t. So therefore, once you grab a calculator, you'll find out that t is equal to 9. Now let's interpret this. T is the time that it took for Sarah to catch Lynn. So it took 9 hours for Sarah to catch Lynn. Well, let's see. If Lynn left at 2, and now this is not part of the question, they're not really asking, but this could be asked of you from your instructor. Lynn left at 2. Well, ... 3 hours later, Sarah leaves at 5. And then ... right? Sarah finally catches Lynn, but it's 9 hours later. Well, 9 plus 5 is 14, so that's 2 a.m. And catches. Now, obviously, we have to assume that San Francisco is pretty far away for this problem to be realistic, because if San Francisco is only 15 minutes away, then it wouldn't take that long to catch her. So we'll assume they're on the other side of the country. Okay, that's a very dedicated friend. So let's try an example that has a different kind of formula to it. Let's see, we have a business that wants to attract more customers and get rid of their stock of paint. And they decide to raise the price. So let's say 6 months ago they raised the price, and now today they offer 25% off sale. Or maybe let's say 6 days ago they raised the price and then offered 25% off sale. This tactic has been used in the past. So by what percent must they raise their original price of a gallon of paint, which is $30, so that it will again be $30 after the 25% discount? In other words, They originally have a $30 price tag on that paint, and they're going to increase it by a certain percentage, and then a couple days later say, hey, we'll give you 25% off of that, and actually sell it for $30, which was their original pricing. So, and then I have a little hint here. What's the price they raise it to? So, first of all, we've read the problem. We understand what's going on, hopefully. Second thing that we need to do is, let's see, it says by what percent must they raise their original price of a gallon of paint? So by what percent? So that tells me I'm looking for a percentage rate of increase. So let me let R equal percent markup. That's what they're going to mark it up by. That's before they're going to give you the discount. Third thing we're going to do is build some expressions or equations. All right. And I give you this hint, what's the price that they raise it to? Well, let's start this out and see what happens. And perhaps the best way to approach this is maybe to use a little bit of logic. The first thing I'm going to do is mark up. So we'll have some type of equation or expression for that. Then, after they mark it up, they're going to mark it down. Right? That's the discount. That's the sale. They mark it up prior and they mark it down after. So let's talk about how to do this. Let's say that you have a $100 shirt. So this is an aside. Maybe I'll even open a new page for this. As an aside, let's say that you have a $100 shirt that you're going to mark up by 10%. I choose these numbers on purpose. What is the new price? Now, a lot of people are very quick with this because they're easy numbers. They say it's $110, right? But the question is, how did you get the $110? Oh, some people say, well, 10% of 100 is $10. But that's not how you got $110. The way you got $110 is you said, oh yeah, 10% of that $100, but that's $10. That's not 110. So you found out what that was and you tacked it on to that $100. So you had this old price, you added to it the percentage rate of that old price, and you got a new price. And so the new price here would be $110. That's kind of an important method, I suppose. You should always remember that if you're not sure how to do something, make the numbers easier, something that you can handle in your brain. So now, suppose instead that the shirt was $37 and they marked it up, let's go for 8%. To find the new price, well, it was $37, right? And you tack on to that old price of $37, 8%, but not just 8%, because that would be a funny statement. You just $37.08. That doesn't make sense. So it's 8% of $37. That should be your new price. Now that I've started that, I have to actually finish it to find out what the actual price is. So let me go ahead and do that. So clear this out. What is it? 37 plus 0.08 times 37. 39.96. Okay, I had to do that just because I have to finish problems. So that's how you figure out markups. Is that you have an old price plus percentage of the old price becomes the new price. So let's go ahead and do that. The markup here, we have this old price, and we're going to do a certain percentage of the old price to become the new price. All right, well, let's see. The old price here was $30 plus, we don't know how much we're going to mark it up, right? So that's just going to be R. That's our percentage that we're marking up, but we still know the old price is 30. And we have no idea, actually, they didn't tell us what the new price is, did they? No, so I'm just going to say that equals some new price. Sad but true, that's the way it is. So here's one equation. Now we have to deal with the markdown. So let me go ahead and talk about the markdown. Again, on the same sheet of paper, because I think that it's important to see this. So let's say you have a $100 shirt again. Again, I'm using nice numbers, and you mark it down by 20%. Well, the new price, what is it? If you have a $100 shirt and it's marked off 20%, well, everybody or most people know it's going to be $80. And you ask why, and they say, well, 20% of 100 is 20. Well, that's not why. You had a shirt that was $100 and it lost 20% of that $100. Notice how that worked. Markups, you're adding. Markdowns, you're subtracting. That should make sense. That comes out to 80. And so if you had, let's say, a $37 shirt and it got marked down by 8%, well, then it started at 37, but you're losing 8% of that 37. Now, I can't leave that alone again because it's just too tempting to finish that out. So let me figure it out. See, 37 minus 0.08 times 37. Notice these look exactly the same except for the plus and the minus. One's a mark up, one's a mark down. 3404. $34.04. Well, that makes sense, I guess. That seems to make sense to me. So let's use that logic here. By the way, it means that to figure it out, what a markdown is, you take the old price and you're going to lose a certain percentage of that old price to become your new price. Oops, there should be an equal sign there. Let's go back here. So the markdown. We have some old price. Well, wait a second. It's just been marked up, right? So, oops, I hit the wrong button. This new price, they're going to save that price for a day or two, and then they're going to say, hey, we're going to mark it down from this new price, right? So they're going to take that price and they're going to mark off a certain percentage, and they told us what percent they're going to mark off. They're going to mark off 25% of that price. And this, they want, after that markdown, they want it to result in $30. Now, this is a tough problem. This is not one that's very common. But I want to show you kind of, because most people say, well, they mark it up by 25%, so that when they mark it down by 25%, it's back to $30. But it's not true. So here we go. I have this word, it's the new price. That's what we're going to insert in there. Well, we have two equations, right? And if you remember from elementary algebra, if you have two equations, you need two unknowns. And I do have two unknowns, r and new. New is okay as a variable. That's fine. It's a picture, isn't it? So we'll go ahead and instead of writing the word new there, we'll replace it with this picture, 30 plus 30r. Right? Isn't new the same as 30 plus 30r? From that, we're going to lose 25% of new, which is 30 plus 30r. And that will equal 30. I'm just stealing this equation right here and inserting, instead of using the words new here, I'm inserting, for these words new, the expression right here. This is the left-hand side of this equation. All right. So in this equation, how many unknowns do I really have? I mean, how many different variables do I have? In reality, I only have one. I have r's. Okay. I'll highlight them for you. There's an r right there. There's an r right there. There's two r's, but the fact is there's one. It's just once we get them together, there's only going to be one of them. So we'll clean this up, clean up each side. 30 plus 30r. There's nothing to really clean there. Minus, and then I'm going to distribute this 25% here. I think that it's going to be 7.5. And remember, the negative also distributes, so it's going to be a negative 0.25 times 30, and another negative 0.25 times a positive 30r. So that's also going to be a negative 0.7 or 7.5r. Combine like terms. So let's see, 30r minus 7.5r is a 22.5r, and then a 30 minus 7.5 is again a 22.5. Subtract the 22.5 from both sides. And this is just, now I'm kind of speeding up because I know how to undo. Whoops, that's 22.5. I know how to undo or untie the knot, right? So I'm just going to subtract 22.5 first. I'll get 22.5r is equal to 7.5. And then finally, I'll divide both sides by 22.5. And remember what I've said in the past, that this is not proper to write your answer as a fraction with decimals within it. You must grab a calculator and use the calculator to change this. 0.333 on forever. So in other words, this is roughly equal to, well, actually maybe I should just say it's exactly equal to 0.3 on forever. Now what does that mean? Well, we found out what r is. It's the markup. They were asking, what's the markup? Well, r is 0.3 on forever, or in other words, a 33.3% markup. Now that's counterintuitive, isn't it? You have to mark it up by 33 1/3% so that when you get a 25% discount, you're back at the original price. Interesting, isn't it? So there's a visual way to think about this, and I don't know if I can actually make it make sense, but I'll try. Think of like a cylinder of liquid or something like that. If you're going to take only a quarter of this, like 25% of this, so that would be this amount right here, all of this, okay, down below here. If I were going to take 25% of that and put it on top as well, I would end up with something about that tall, roughly, okay? And then if I were to take off 25% of this, well, 25% of that might be maybe about this much. So if I chop that much off of it, look what I've done. That distance is not very big now, right? It's actually smaller than the original cylinder. So what you have to do is you have to take a bigger percentage of the original cylinder. So let me just start over again. Here's the original cylinder, let's say. 33% of this cylinder is up to here. So this is 33%. So I'll take that cylinder that was up to this height, and I'm going to tack on another little bit. I'm using the lines on the paper to help me kind of illustrate this, by the way. This one was 3 lines high, so I took 1/3 of it. I stacked it on, so now it's 4 lines high, right? If I cut off 1/4 of this, look, I have 1, 2, 3, 4 sections. If I cut off 1/4, aren't I back up to down to the original size? Yeah, strange but true. That's the way it is, and that's actually the first time I've actually illustrated that properly, I think. But the lines on the page help out. Take 33% of this, and that's basically taking one of these lines, line widths, and you're tacking it on top. Now you have something the size of 4 line widths. If you take 25% of that away, you're back to the original. Huh. Fun. We're approaching the last 2 examples. This one is just a fairly typical one, and actually in a previous lecture I approached this style of problem. You have somebody that wants to know what he needs to get on the last exam to reach a 70% average on his total exams. And his previous exams were 65%, 78%, 54%. Find the minimum score he needs on this last exam to average 70%. Now, I've read it, I understand it. I'm going to let X equal fourth exam score, because that's the only thing that we don't know. And in fact, they even ask us what's the minimum score he needs on his last exam. So there we go. We'll just say that. And now the third thing is to write some type of expression or equation that involves this variable. Well, this is an average. Averages say you add up the scores and divide by the number of scores. But that's just the average. I want that average to at least be 70%. There's a couple ways you could do this. You could put a greater than sign here, because that technically would be the right way to do it. But since we haven't really talked about inequalities yet, I'm just going to find out when will his exam score be exactly 70. All right, so let's go ahead and do this. This equation involves a fraction, so the first thing I will do is multiply both sides by 4. So let me go ahead and group this side and group this side and multiply both sides by the number 4. On the left hand side, 4 over 4 becomes 1, so that's kind of gone. And so we get 65 plus 78 plus 54, and offhand I just have to figure that out. So let me turn this calculator on, clear all this junk out. 65 plus 78 plus 54. It's 197, so I'll go ahead and write that in here. 197 plus x is equal to, and 70 times 4 is 280. Subtract 197 from both sides. And we get x is equal to 83. So he will need an 83% to pass. Ooh, that's my dog. As a very final example, we're going to go ahead and take what I consider to be a mixture problem here. A manufacturer of soft drinks advertises their orange soda as naturally flavored, although it contains only 5% orange juice, and that's pretty often the case. A new federal regulation stipulates that to be called natural, a drink must contain at least 10% fruit juice. Unfortunately, this company has a vat of this 5% orange juice left. So how much pure orange juice must this manufacturer add to their 900 gallons of already mixed orange soda to conform to the new regulation? Okay, so let's go ahead and state that we've read it and understand it. Let's also label the unknown here. How much pure orange juice? Aha. So that must be the thing I'm looking for. The thing I'm looking for is how much pure orange juice. So we'll choose a variable. O is not a good one. So maybe I just should do P, I guess, equal amount of pure OJ that's added to the to this thing. Okay, and now the third step is to write some equations. Now, what I'm going to do is I'm going to draw a picture here, because drawing a picture does help out with these type of problems. You could think of this as mixing two vials of liquid, each having a different percentage mixture. If you think of it that way, it really does make your work a little bit easier. So let me draw a vat of liquid here, and I'll draw another vat of liquid next to it, but let me at least do this. This is what they have on hand right here. This is currently a 5% mix, and they have 900 gallons of it. And you can think of this, how this would be labeled when you walk in. You see this big vat, it says 900 gallons and it's 5% mix. And to that, they're going to mix in a certain amount of pure orange juice. So this is pure. And by the way, pure orange juice is not mixed. It's 100% 100% pure. And we just don't know how much of that, how many gallons of that. We have P gallons of this that we're going to mix in there. We have no idea how many gallons that is though. But when you think of this as picking these two things up and mixing them together, it should come out to be a brand new vat, maybe slightly larger, right? You don't have to actually draw it to scale slightly larger or anything. I'm just saying it should be. It makes sense that it would be slightly larger. And this should be, by federal regulations, 10%. 10% OJ should be here. 5%, maybe I should say OJ should be there. And the amount of gallons in this vat, this mix in the end, should at least be the 900 that we started with, right? Because, right, we were taking all these 900, and then in that we're also mixing an extra P amount, so plus an extra P. If you draw these mixture problems like this, it makes your life super, super duper easy. Because essentially your equation is staring at you in the picture. What you do is you multiply these two numbers. And the reason, I'll give you the reason in a moment here. You multiply 0.05 times 900. Now, here's the reason why. If there's 900 gallons of liquid here, and I know 5% of it is pure orange juice, that means that 0.05 times 900, or in other words 45 gallons of it, is pure orange juice. This is the amount of pure OJ in that vat, if you could sift it out. Plus 100% times P. 100% as a decimal is 1.00 times P. And that's just multiplying these two numbers together. And the part that most students forget, you also multiply these two numbers together. If you did it on the left-hand side of the equation, of the equality, then you'll do that on the right-hand side too. It's 0.10 times 900 plus P. And what this is going to be is the amount of pure OJ in the final mix. So we have the amount of pure OJ in this 900 gallon vat. We have the amount of pure OJ that we're going to add. And then we end up with the amount of pure OJ in the final mix. And if you look at this equation, I can now zoom in on that and do my mathematics here without worrying about the rest of the words. So 0.05 times 900 is going to be 45 plus P, that's just 1 times P. And over here, 10% of 900 is 90 plus 0.1 P. And if I'm going to, I forgot my implication signs. If I'm going to gather all my variables on one side, I'll subtract 0.1 P from both sides. And this will give me, maybe I should point down there, 45 plus 0.9 P is equal to 90. Subtract 45 from both sides. So you get 0.9 P is equal to 45. And finally, divide both sides by 0.9, and you'll get the following. Let's see, this 450 divided by 9, which is 50. All right, so this tells me that P is 50. So how much pure orange juice should this manufacturer put into their vat so that they meet federal standards? 50 gallons. 50 gallons of pure OJ is what they're going to add in. And that will increase the concentration from 5% up to 10%. This picture, by the way, is a great picture to use for mixture problems. So mixture picture. It works whether you're mixing peanuts and cashews or you're mixing a 6% acid solution with a 13% acid solution to produce a 12% acid solution. It works for all of those problems.